So when incident waves strike the boundary, they produce refracted waves, those are the red ones, and reflected waves, those are the blue ones. So now we show this happening with incident waves coming in, hitting the boundary, producing reflected waves and refracted waves. The color scheme of this diagram is a little bit different. The incident wave is red, coming from the upper left. The reflected wave is also red. The refracted wave happens to be blue here. But what's happening is Huygens' principle is showing us the creation of the new wave fronts. And the difference between the incident and the refracted material is the speed of the wave. When the wave changes speed, then the speed of the wavelets change speed as well, and that's what causes the bending. We care about Huygens' principle because when we come to talk about Young's double slit experiment, Young's model of what happens is based on Huygens' model. He's going to use Huygens' principle in order to be able to construct secondary wave fronts that are going to interfere with each other. Now we want to move on and discuss Young's experiment. If someone were to come up to you on the street and ask you, is light a wave or a particle? You might answer, well, light can behave as a wave or a particle. If they come back to you and say, how do you know? What's the evidence? Then for the wave property, you ought to cite Young's double slit experiment. How do we know light behaves as a wave? Because of Young's double slit experiment. That is going to be a question that you're likely to face on the AP exam. This is such an important point, I'm going to stress it again, and you should write it down. How do we know light behaves as a wave? Because of the results of Young's double slit experiment. You need to know what Young's double slit experiment is. You need to understand its geometry, and that's what we're going to talk about right now. Young's double slit is a demonstration of the interference of light. Let's cast our mind back to review interference. We have two types. There's constructive interference and destructive interference. And this sort of interference can be demonstrated with any kind of wave. It's not just a light wave. It can be done with sound. It can be done with water waves. And I have a simulation that I would like to show you about something called a ripple tank. I want you to imagine that this gray rectangle is a surface of water. And let's suppose that I start dipping my finger up and down in the water to disturb it. And when I do, if I do it regularly, then I'm going to form a ripple pattern that's going to spread out throughout the material. This ripple pattern produces waves that are traveling outward from the source of the vibration, and they travel with a certain speed. We're going to stop this for a moment, and we can see that in this diagram there are crests, which are indicated by the green, and there are troughs that are indicated by the pink. There are certain wavelengths that are there, so you could measure with a ruler the distance between the crests or the distance between the troughs, and if you had a stopwatch and a ruler, you could actually measure the speed of these waves. Now suppose I have two sources that are going to vibrate in phase with each other at the same time. What's going to happen? Well, let's see what happens. Here I have two sources that are vibrating with each other in phase. They're going at the same frequency, at the same rate, and what happens is there's a ripple pattern that's produced up, some places where there is constructive interference, other places where there is destructive interference. I'm going to rotate this view just a little bit. And now let's stop and look at this particular pattern. What I want you to see is that there are regions where there is green that has large amplitude. Those are places of constructive interference. And there are places here in between those that have destructive interference that are colored gray. So that there, if I had a viewing wall that was at the back of this pattern here, I would see that there would be large amplitude vibrations that happen in certain directions, and there would be hardly any vibration amplitude at all happening in other directions. And so what we are looking at here is an interference pattern that's produced by these waves. The place where the green waves are striking are places of constructive interference. The place where there are gray, that is regions of destructive interference. And what we want to do now is to see, does light behave in this way? So here is another simulation. In this simulation, I have a source of light, and this source of light is going to produce waves that are of a certain color. These happen to be red here. I like this red because it looks like the red of a laser that we'll use in the classroom. Now, according to Young said if I had two sources like this, I could produce an interference pattern. Over here on the right of this diagram is a wall that is going to receive the light. What I want to do now is to show two lights that are vibrating with each other. I'm going to space these lights out a bit, and we're going to see what would the pattern of two sources of light look like if the light behaved as a wave. And what I want you to see over here on the right is an interference pattern in which there is a bright fringe that's in the middle between these two sources. Then there are dark fringes on either side. Then there are bright fringes, and then dark fringes, and then bright fringes, and dark, and we get an alternating pattern of light and dark spots on a wall, a viewing wall, if we have these two sources. And what Young was able to show is that this sort of pattern happens with light. And since this pattern happens with light, since it undergoes interference, then light must be a wave. In 1803, Thomas Young demonstrated this, and now we want to look at the geometry. The geometry is something that's going to be important for you to understand, and this that is about to be sketched here is going to be a very busy diagram. The diagram is something that's sketched in your textbook on page 550. We're going to sketch it here. In Young's double slit experiment, we have an opaque mask that's going to be placed in front of some source of light. So over here off to the left, there's going to be some source of light. In the laboratory, we're going to use a laser as our source of light. And we have these two slits here that are in this opaque mask. These slits are separated. Their center-to-center distance is a distance that we'll call little d. This diagram is greatly magnified to show the geometry, but generally this little d is very small. It's on the order of a fraction of a millimeter, maybe even 1/100th of a millimeter, depending on how the manufacturer of the slits is. Off to the right, we have a viewing screen, a wall, if you will, on which we're going to observe this interference pattern. The wall is going to be separated from this opaque mask by a distance that we'll call capital L. Now, if light falls on these two slits and then is allowed to progress to the viewing screen, what do we see? We see a pattern of bright fringes and dark fringes. I'm going to represent those as spots. If I look directly from the middle of where those two slits are, I see that there is a bright spot. And then above and below, or to the left and to the right of this central maximum, then we're going to see another series of bright and dark fringes. We're going to label these spots with numbers. We're going to call the central one M is equal to 0, and we'll talk about M in just a moment. That's going to be known as an order number. So we have the M equals 0 spot in the very middle, and then on each side we have the first spot, M is equal to 1. We have the second spot, M is equal to 2. And depending on what the geometry is, you might have 10 or 12 or 15 or 20 or 100 fringes. Sometimes you'll only have 2 or 3. What I claim is these bright spots on the wall are places where constructive interference is going on, and that in the spaces in between, in the middle between the bright spots, are places where destructive interference is going on. So now, how is this constructive and destructive interference set up? I want to choose to look at one of the spots and look at the light that comes from each of these two slits that strikes that spot. Let's look at the m=2 spot on the top side of the screen. There's a wave of light that I've indicated in blue here that travels from the top slit up to that point. There's another wave of light that travels from the bottom slit up to that point as well. There are waves that are traveling to those 2 points, and we say that those 2 waves interfere with each other constructively. So what? Well, here's the so what. The light from the top slit has traveled a shorter distance than the light from the bottom slit has. How much different distance has it traveled? Well, we can actually construct that. If I were to drop a perpendicular line down from the top slit to the bottom line, then I could construct myself an isosceles triangle. And what I claim is that once I have constructed this line, which I've sketched in pink here, that the distance of the blue line and the distance of the orange line from where this isosceles triangle has been made, those 2 distances are the same. So the little amount that's left over is this little extra distance right here. In other words, this little extra distance is how much farther that light from the bottom slit travels in order to get to this spot, this bright spot on the screen over here, the m=2 spot, than the blue ray had to travel. Well, now how much is that distance? If I look at this little triangle right here, and I call this angle between the opaque screen and this line that I constructed theta, then I see that in this little triangle, D is the hypotenuse, and the extra distance is going to be the opposite side of this angle. So this extra distance here is equal to D times the sine of theta. Now here's what I claim. I claim that if that little extra distance is equal to some integer multiple of the wavelength of light, then I will get constructive interference over here on this viewing screen. I'm going to get a bright spot over there. And if we're looking at the second bright spot, then what that means is that there must be 2 extra wavelengths in this little extra distance. Let's write that condition down. And this condition that we're about to write down is at the heart of Young's double slit. It's important for you to understand that. So let's write this down. The little extra distance is this d sine theta, and the number of wavelengths has to be an integer if I'm going to get constructive interference. This is the heart of Young's double slit understanding. And likewise, for destructive interference, the places where there are dark spots on the screen, that means that there is a half integer. When I have a half integer number of wavelengths in this little extra distance, then what's going to happen is that the crests from the blue line are going to overlap the troughs of the orange line. In other words, the crests from the waves that come from the top slit are going to overlap the troughs that come from the bottom slit. Or likewise, I could have troughs from the top interfere with crests in the bottom, and I'm going to get destructive interference. Okay? So, these are the conditions for constructive and destructive interference in Young's double slit experiment. Now, sometimes it's not easy to measure these angles because these angles tend to be very small. How could I measure other distances? Let's go back up to our drawing a moment and sketch some things. First of all, I want to sketch a line that goes from the point that's between the 2 slits over here to the place where the bright spot is. This diagram is about to get very busy. What I claim is that this triangle that includes this line that I just sketched, that goes down to the zeroth order fringe and across to the middle of the slits. That green triangle is a triangle that is similar to the triangle that includes our little extra distance there that has the d sine theta. In other words, this triangle right here, this gray triangle. Now how can I say that? What I claim is that this angle that we called theta in the small triangle is going to be the same as this angle here